Hey guys, what is going on? Thank you for all of your support. We are now starting a playlist on quantum statistics. Don't worry, my other playlists are nowhere near done as I aim to continue those in physical chemistry and twistor theory and so much more, quantum field theory, and all of that. As more and more of you contribute to the channel, I will be able to produce more and more content. Again, my aim here is to provide high quality advanced science, not just the basics, which is what every other channel does when it comes to teaching science on YouTube. The animation that you are seeing here is a system of dynamic spin up and spin down states, and as we continue with this playlist, we will aim to understand such systems in using ideas of quantum physics, and we are going to get pretty advanced and nuanced into this topic. So without further ado, let's start with quantum statistics. Really quick, I want to make sure to notify you guys that if you go onto Patreon, you will be able to get the notes for these videos and so much more. So in the notes, again, if you want to contribute, you can. If you want to contribute, you will get those notes. But also in those notes is going to be more than what I just do on the iPad. There's going to be example problems in the notes. Everything's going to be fleshed out in gory detail so you can understand the basic derivations and the math behind the stuff that we're going to do. So everything I would do on the whiteboard is also going to be on the notes, okay? But there's going to be more on the notes because it's a lot easier to make those notes than it is to make the videos. It takes some time to make these videos. So I just want to start with a bird's eye view here. What is quantum statistics? Well, quantum statistics is a very interesting area of study that attempts to understand classical systems in terms of quantum states. So things like spin, for example, we want to understand multi-particle systems, but in terms of the spins of those particles, right? And spin fundamentally is a quantum property of electrons. And from an even larger perspective, or a larger, more higher up in elevation bird's eye view, this is going to be really, really useful for, say, those of you who are into healthcare, for example, because as you might understand, MRI machines probe the spin of these particles, and there's many of these particles in our bodies, and so understanding quantum statistics will give us some insight not just into the physics of things, but also how we can understand biological systems as well and apply this understanding to healthcare. And so we might be able to understand something like the net spin of a classical system, and we might be able to utilize that to our advantage. Again, when we're looking at MRI machines, or when we're looking at the physics behind MRIs, we are looking at the net spin of some tissue, and the rate by which spin relaxes back down to its original state is something that you typically go over in MRI physics. But I don't think we're going to really get into MRI physics in this playlist. That's going to be a topic for a separate playlist. We are also interested in understanding the question, at what point does a classical system become, or at what point does a quantum system become classical? And we're going to be able to understand all of this in terms of something called a density matrix. This density matrix is going to be an n by n matrix. We'll understand what n means later as we get more into the math of things. But this matrix is at the core of quantum statistics itself. Just like the metric tensor is at the core of general relativity, the density matrix is going to be our go-to thing for understanding multi-particle systems and understanding those systems in terms of quantum states, again, such as spin, quantized energies, quantized angular momenta, and so much more. And it's going to be important to understand that for the density matrix, that thing acting on some operator sandwiched in between two eigenvalues of that operator is going to give us something quite interesting as well. We'll be able to understand what average means in terms of these quantum systems as well. And so quantum statistics is very, very important and very useful, especially when we begin to couple it with ideas in statistical thermodynamics. When we get to that point, we'll be able to understand how thermodynamics can help us in probing or understanding the quantum properties of many particle systems. We will also be able to understand both of these if we also couple in ideas with nonlinear thermodynamics as well. Nonlinear thermodynamics is a whole other area of science that attempts to understand sort of how systems evolve in time, what the probability is of them evolving within a certain trajectory in time, but not in equilibrium, right? So in statistical thermodynamics, we are typically dealing with things in equilibrium. In nonlinear thermodynamics, we are dealing with systems that are not in equilibrium. And when we sort of take all of these ideas together, we get a very strong and powerful framework for how we can understand multi-particle systems, not just at equilibrium, but also at not equilibrium. And this is going to touch into areas of chaos theory and so many other areas of science that it's going to our general intelligence is just going to explode. And so with that being said, let's go ahead and dive into some more of the hardcore math. We're going to do some proofs. We're going to really understand the density matrix. And we're going to do this on the whiteboard. All right, so we are now at the whiteboard. We're going to understand some things about the density matrix. We're going to cover its basic properties, and we're going to get into understanding this also pictorially. We have some images here on the whiteboard. Again, you can find all of this and more on my Patreon page if you become a member there just for $15. Again, you don't just get the stuff in the quantum statistics notes, you get everything, right? So if you're someone who's interested in not just quantum statistics, but general relativity and quantum field theory, you get those notes as well, and those are constantly updating. So it's not like you pay for something and then that's all you get. You pay for this thing and you get that, plus more and more updates. I'm going to be correcting things, I'm going to be adding, I'm going to be subtracting things. I want to really make these notes, they're not really notes actually, they're more like it's kind of like an evolving textbook, if you will. So with that being said, let's go ahead and let's continue with this density matrix stuff. All right, so this is again just a general introduction or gentle introduction into quantum statistics. We're going to go through some detailed derivations here. Again, I'm trying to make this as digestible and easy to understand as possible. So we're going to start our discussion of quantum statistics with something called the density operator or density matrix. We're going to understand this as a matrix as we go on. And this is going to be the key player in understanding the topic, like I've mentioned before. Again, just like the metric tensor is to general relativity, the density operator is going to be as important as that here in quantum statistics. So suppose we have some system of moving particles, and the system of moving particles, again, we can just zoom in on this, looks like this. Again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles in this system, okay? And we can create an ensemble from this system. So what is an ensemble? Again, I'm going to bare bones here. So an ensemble is going to be copies of that system. So you might hear people oftentimes, or in the literature you might read copies of a system, or the copies, or the copy is sort of what you read or listen or hear at least what I hear most of the time when I read this stuff or listen to lectures on this stuff. But we have different copies of the system, and how does this help us? Well, in classical physics, such an ensemble is understood in terms of momenta and positions of the particles in the system. We could, for example, say that each copy of the system has an average position of particles, and each copy has an average momenta also. So we have this copy here and this copy. These look the same, but then we have this one. The particles seem to congregate in the corner. We have this copy of the system in which the states are sort of clustered in different regions as well. And then we have this guy right here, which is also, the particles seem to favor the border of things, right? This might be a membrane, for example. We might have proteins that favor the membrane, right? But again, proteins, you'd have to find a quantum state for that protein as we go on and understand this, because we're doing quantum statistics here. Okay, so these are all different states that have their own probabilities of occurring. And we denote this probability simply as P sub n at time equals 0. Okay, and so this is the fraction of the ensemble in the classical state, n at time equals 0. All right. In quantum physics, we don't really make that much of a logical leap from here. That is to say that instead the probability of representing the classical state, we have it represent a fraction of the ensemble in a quantum state. So we might picture something like this, for example. So we have our system. It has 5 particles in it. And the particles have this thing called spin, right? So if you're not aware of what spin is, it really fundamentally comes down to it's an internal degree of freedom, and it comes from different representations of the Lorentz group. That is something for quantum field theory. I touch upon that in my Twister playlist also. And so if you're not aware with what spin is, all you need to know for right now is that spin is an intrinsic property of a particle that is binary. It's either spin up or spin down. Okay. There's other internal degrees of freedom that we'll be able to understand for other different types of particles, such as color, for example, and quarks. But right now, we're just going to deal with spin. That's the simplest sort of quantum property that we can sort of think of right now. So we have 2 boxes here, where we have 2 copies here, in which we have 3 upspin particles and 3 particles that have downspin. Okay, and same thing here, 3 upspin particles, 2 particles that have downspin. So within our entire ensemble, the fraction of the particles that have spin up, or net 1 spin up, right? So we can think of this as 2 of these are going to cancel out with like that. The net is 1 spin up. This here, the net is 1 spin up as well. So 1 spin up particle, or our system with 1 spin up, with 1 net spin up particle, is going to have a fraction of 2 over 5, because we have 2 copies within an ensemble of 5 copies. All right. And then we have the same thing here, right? So for 5 downspins, the probability is going to look like this. And then same thing, we have 3 downspins and 5 upspins. All right. And so this is how we are going to understand this probability. The probability is a fraction. And so it's going to be related to the likelihood by which we observe this system. Okay? So this can be more generalized now. Suppose that we have n total copies of our ensemble, and we allow for a more general way to write down our quantum states. So instead of having 1 up, 5 ups, 2 down, 3 down, whatever, we're just going to call this psi. And suppose we have 3 copies of psi, of state psi, and we have psi 1, and then 5 copies of psi 2, and then 1 copy of psi 3. Okay. And so, again, suppose this is at time equals 0. We're supposing for everything right now that time is equal to 0. And when we do this, this is going to be our probability. So psi 1, right? So we can sort of think of the 1 here as the 1 right here, right? So this 1 right here is this 1 right here. These 2's are right here. This 3 is right here. So the probability, the way we can read this is that the probability of seeing state 1 for our system at time equals 0 is going to be 3 over n total, and n total is the number of copies of our system in our ensemble. All right. Okay. So notice something, that the sum of Pn at time 0, or at any time, is 1, right? So from this, it's fairly easy to infer some basic properties here, that P sub n of 0 is always greater than 0, right? Because these are fractions. They're not, if you can't have an ensemble with 0 copies, unless you invent some copy that the ensemble can never have. But this is always going to be greater than or equal to 0. Okay? It's going to be equal to 0 only if the numerator is 0. So if there's copies in our ensemble that just don't exist, well, then that fraction is going to be 0. All right. Again, however, you could have copies that become attainable later on in time. So that's going to be something to think about as well, but are not sort of present at time 0. Right? So it's key to understand that this is going to be greater than or equal to 0. But it's also key to understand that the sum of the fractions is going to equal 1, right? Because here we have 3 plus 5 plus 1, and that's going to give us n total, right? Because we have up here in this example, for example, we have 2 plus 1 plus 1 plus 1. That's 2 plus 3, that's 5, and the total copies in our ensemble is 5, so it's going to give us 1. All right, so far so good. We're going through this pretty slow because we want to build a firm and strong foundation for quantum statistics. Okay, so we can compare the average of some observable in the quantum case and compare it to the average of an observable in the classical case. So when we calculate averages again, this is sort of the prescription we make. We've talked about this before when we talked about statistical field theory, and ideas in statistical field theory are going to come up as well. This is going to be, these videos are sort of in the making, and I'm thinking about maybe merging this with statistical field theory, and so we'll see how that goes. But anyways, this is the average. Here we have E sub n, P sub n. It's a sum, right? So this is how we calculate the average classically. Contrast this to quantum now. This is how we calculate the average of some observable given some operator A. And so this is how we're going to calculate that. Okay. So the probability of going from this state to this state with this operator multiplied by the probability of being in the state is going to give us the average of that operator. Again, this is something that you've probably seen in quantum mechanics. I'm assuming that you've sort of understand some basic quantum mechanics, some basic statistics, probability, and so forth, so that we don't have to really start from square one. But so now in the classical case, we are summing just over the probabilities of some scalar value that describes the system. So that's this case right here. Energy is probably the easiest thing to conceptualize. You can ask the question, again, what is the average energy of some classical system? And you just use this prescription to calculate that average energy. But when it comes to quantum systems now, because now we're looking at we're looking at quantum states like spin, this fully fleshed out looks like this. So we can have, the probability of going from spin up to spin up is going to be this, sorry, my bad. This is the probability of us being in spin up multiplied by the magnitude of, multiplied by this number here, right? This is an operator acting on this vector here that represents the upstate. And then we have this ket vector here, or the bra vector. Multiply that, and that's going to give us a number. That's going to give us the probability amplitude of going from state up to state up, given this operator. And then same thing here. So this fleshed out is just, you might ask the question then, okay, what about from going from state up to state down? And we can do that, right? But the problem is going to be that n here is, n right here is, this is going to be m, right? This is going to be state m to n. And here we only have an n. So this is where the density matrix is going to start helping us out. Okay, but before we get there, the specific cases are always very easy to understand. So let's do this now. In quantum mechanics, we want to say that an operator A is Hermitian, which means that if we have eigenvectors A here, our operator A here, we can say this right here, right? So if this is an eigenvector of A, then this here is going to be an eigenvalue of A. This is, again, basic quantum mechanics stuff. The reason I said the reason I put this again is because this is a very tangible example. And so, okay, so with this in mind, we can rewrite the average observable in the following way. So we're rewriting this now using this idea. And so we get this, right? So what we're doing here is we're taking A alpha, right? So we're doing this right here, or this here is what's known as the completion relationship. And that's when we do this, make sure my pen thickness is okay. When we do this sum here, A of A like this, that's going to be 1. This is something that you probably should have seen in quantum mechanics. This is what's called a completion relationship. So when we do that, we're just really multiplying by 1 here. We're not doing anything. But when we do that, we get this guy right here. And this guy right here is going to be A acting on A is going to give us this here, right? Because that's right here. And so we get this, right? And so this times this then, well, this is just this squared, because it's psi n times A times psi n. This is the probability to find an observable in the quantum state psi n. This is what is unique to the quantum aspect of things, okay? This is going to be, this here is what quantum statistics is going to be based off of, okay? And we're going to see how this is going to be related to the density matrix. And this here is just the probability that we observe the state and the psi n itself. All right, so again, this is the probability to find an observable from this operator, right? So again, because A is an eigenvector of the operator, so A here is coming from our operator. Psi n is the quantum state that we're interested in. All right, as we continue, such an observable operator can be a momentum operator or a position operator. Again, this is very general. We're not going too deep into any specific thing quite yet. So with this in mind, we can see that we need to take into account the probability of finding a particular spin state and a particular spin state and a particular spin state with some momentum at some position. Okay, and so we're able to rewrite things now. So if we just take this, we can rewrite it in this way. And then we take this here, and we can see, again, that this here, if we take this Pn and these two guys right here, we can see that that's this right here. Okay, and then the rest is left out. This is what we're calling the density operator. So this right here is the core of everything that's going to come from statistical mechanics, okay, or quantum statistics. My bad. All right, so this is what we're going to define as our density matrix, and this is the central object in quantum statistics. Similar to how the metric tensor is the central object in Einstein's theory of general relativity and so on, this thing is going to be the central object in quantum statistics. The density matrix holds the probability of all the possible quantum states of the system, whereas the operator holds the defined observables that we can make about the system. So here are just some example. For example, observables. That's not my pointer. And these observables are going to be all these guys right here. Or these guys right here. This is their symbol. This is another way to write their symbols as operators. And then explicitly sort of drawn, like typed out here, we have all this, okay? Here, x is just multiply our system by x, multiply our state by r here. And so you could take a look at this. This is in the notes, right? All of this is going to be in the notes. And this is, these are the observables, right? So when we write a down right here, so this a right here, that is going to be, when we look at, we can look at this table here to get understand what we might want to put in for a. So for a can be, for example, this right here, or a can be the total energy. It can be our Hamiltonian, right? So we can put our Hamiltonian in here. This is going to be our total energy, okay? But this table gives us an idea of what a could be, depending on what kind of situation we're interested in measuring. All right. These are all possible forms that the operator a can take. Rho, on the other hand, is a unique operator that does not look like any of these operators mentioned in this table. Rather, the rho operator is going to be a matrix that contains the probabilities of fractions of quantum states in an ensemble. So take, for example, a simple two-state system here. We're going to consider the spin of a single particle again, but it's just going to be very, very simple. So again, just one particle. It can be up or down, and we'll say the probability is equal, right? So it's going to be 50% up or 50% down. So our density operator then is going to be 50%. We'll call the up state 0, and we'll call the down state 1. And so so we could say, for example, that 0 here is going to be, if this is our up state, it could be like this, and then our 1 state, if this is our down state, this could be like this. We take the outer product of those two things, and we get this when we multiply by these weights here, right? So these guys here give these half guys here, right? So if there's a 75% chance of having up, then this guy here is going to be 3/4, right? Or 0.075. But the point here again is that, okay, for a very simple system, our density matrix looks like this. Let me erase some of this. Let's continue. So we can notice that the trace of this matrix equals 1. This is a very unique property of the density operator, and so we're going to prove this right now. So we take the trace of our density matrix, that's going to equal this right here. Okay, so the trace formally sort of within the context of its components, m, right? So those are the diagonal components, and the sum of the diagonal components of any matrix is the trace of that matrix. We can use the completion relationship again. Put these two guys in here. We do the sandwiching, and this here is going to be our probability of finding those guys, right? So okay, so from here to here then we get this guy right here. All right, and then from here to here then, this is just a completion relationship again. So we're sort of inverting, so these guys are in the middle, now these guys are in the middle. This is 1 because these are two orthogonal states, and so we get that this sum of all the probabilities associated with these states is going to be 1 because we're summing over all the probabilities. So the trace of our matrix, the trace of our density matrix is indeed 1. We can also show that this density matrix is also Hermitian. And so to show this, we take the dagger of both sides of this, okay? And my bad. So we take the dagger of both sides of this, and we get this guy right here. Because we just swapped these two guys, and these two guys are the same. So this is the same definition as the row matrix. This here, again, this just comes from the definition, right? Just be clear, I don't think I was very clear, but this guy right here, this guy, that came from the definition of row. All right? So even though this density matrix is not an observable for our system, it is starting to look an awful lot like one. We can see here, for example, that if we square row, and again, so if we're just looking at psi 1, we can look at psi 2, 2, or 3, 3. We can look at any of the diagonal entries, but this is going to be a row. And so in the case that row squared is equal to row, we're going to get a matrix that looks like this, because we know that the trace has to equal 1, and the only possibility in which something squared is equal to itself is going to be 1 or 0, but since the trace has to be 1, then this has to be 1 as well. This has to, we need to have a form that looks like this, in which everything is going to be 0 except for 1, and this is what's called a pure ensemble. So in this case, the probability sits entirely in one state for the ensemble. So the properties of this density matrix are going to be the following here. And so now we have all this. This here is for a pure ensemble. Again, my apologies for the dogs. So now we have 3 questions looming over our minds for this density matrix as we proceed forward. The 3 questions are going to be, what do the off-diagonal components of this matrix look like? Okay. How can we understand the time evolution of this matrix? And are there different representations of this matrix, and what do they represent? And that's going to be a very key understanding or a very key thing to address as we go forward with quantum statistics, because the idea of different representations is going to lead us into the idea of what representations of this matrix are going to correspond to the right system that we are trying to model, right? We want to model a system, but we have so many different representations now. Which one is the right one? That's going to be something we're going to address later. And so as we answer these questions, it's going to form the basis of quantum statistics, which is naturally going to lead us to the concepts in understanding condensed matter physics and the quantum many-body systems. To get our feet wet with these advanced ideas and topics, let's consider a multi-quantum state system, and let's consider spin again, because spin is sort of easy to conceptualize in our head a little bit more than, say, energy. Let's consider the same ensemble again. But when we do this now, let's say, we have, this is just an example, but suppose we allow each particle to be either up or down, and so the states that we can have is a state in which everything's down or everything's up, and then we have these in-between states, right? We have 1 in which 1 is up, in which 2 is up, and this could be the net. So this could be the net number of particles that are up as well. So the number of particles that we're considering could be like 1 million particles, but we're interested in what the net spin up is, and so that's what this is going to be. That's what these guys are going to be here. The idea here is that the sum of these bars is going to have to equal 1, okay? Because if we go back here, that the trace of this matrix has to equal 1, that means that these things are going to correspond to probabilities of being in some states, and these probabilities, again, these weights are going to be the probabilities of finding this state in this our system in this configuration. And so this, I think, is a really nice and easy way to understand what the diagonals of these matrices are going to look like. Now the off diagonals are a completely different beast, and so those off diagonals are going to take us a little bit of time to understand. So let's go ahead and now go into some code, because again, I want to not just go over concepts and animations, but we want to get into some code as well. Alright, so what is science without a little bit of code again? So as you've been noticing in these videos, science really entails understanding the theory, understanding the concepts. So we go to the whiteboard, we have animations, but we also want to be able to apply our knowledge in how to use computers to understand and visualize scientific concepts as well. And so the code or the animation that we want to look at here in this video is going to be this guy right here. So when we play this, this is an example of a density matrix. And so when we take a look at this, the matrix itself is right here. Numbers are encoded in heat values, right? So the larger the number, the brighter, more intense the heat value is. And we can see as these, I'll rewind this, as these values move around, the eigenvalues for this matrix also change, okay? And then the eigenvectors as well change in 3D space. And so if we pause this at any moment in time, we have one eigenvector, two, we have a third eigenvector, we have many eigenvectors, and theoretically we should be able to have 6 eigenvectors in a case of a 6 by 6 matrix, okay? And the condition that we're putting on the matrix again is that the sum of the trace of the trace of this matrix, which is the sum of the diagonal components, has to equal 1. Okay, that's going to be a key thing to really hit into our heads as we continue with quantum statistics, is that there needs to be some boundary conditions, and one of these conditions is going to be that the trace of this matrix has to equal 1. Okay, and this matrix is going to dictate everything that we cover in quantum statistics. Let's go to the code just to take a look at a little bit of this. So again, nothing fancy here. We can edit if we want a 5 by 5 grid, 6 by 6, 7 by 7. The idea here is that n is going to really, as we sort of alluded to on the whiteboard, n sort of represents as we allow for more quantum states, or as we consider more quantum states, our matrix gets bigger. The more quantum states we have, the larger the n value we have, right? So we can have a quantum state in which we have 1 spin up, or 1 net spin up. We can have a quantum state in which we have 3 net spin up, or a quantum state in which we have 4, 5, 6, whatever. That is going to correspond to this value right here. We have color maps, we have padding. This is just aesthetic stuff. Is symmetric generate. So this tells us if this is false, we would say that the matrix is not therefore necessarily symmetric all the time. Here I've just said it true. If it's not symmetric, then the trace properties get a little bit weird and we get negative eigenvalues. So we're going to have to make sense of that. But for right now, we're just going to deal with symmetric matrices, symmetric density matrices. Okay, and then we can modulate how much time between each transition is between each numerical values. So when we go back here, these values change, right? And we could dictate the rate by which these values change in some of these values that we put here, right here. Okay. We have a helper function. This is going to create a random matrix with a trace of 1. Okay, and that trace of 1, that is going to give us, that's where we have this epsilon right here, small positive constant, to ensure that all eigenvalues are strictly positive. And, excuse me, so that's what this is going to be here, this helper function. That's what we're going to do all up in here. All right. Okay. If we move down a little bit, create symmetric matrix, and a lot of this is just aesthetic stuff. where we're coloring things. The figure setup, then, we have 3 subplots, right? So we have a histogram, we have a 3D axis, and we have a matrix. The matrix is the 0, 0 subplot. The histogram is the 0, 1 subplot. The subplot is the 0, or the 3D axis is the 2, 0 subplot, right? And so, right, those are just these subplots. Then as we continue, we have this right here, right? So we're just initializing stuff now. I put a lot of notes in here to hopefully make it so that you guys can understand what's going on. Again, code, no one's really on the tier yet for code, and so once people get on that tier, then there'll be more reason for me to actually start posting this code on time, or not on time, but on the Patreon. But then a lot of more aesthetic stuff. This is all just we could change these to make them look different. Animation update function. This is where the animation starts taking place. There's really nothing to change here. This is really everything is really sort of automated in this code, because we're just generating a random set of numbers with the only condition that the diagonal components here are equal. The sum of the diagonals are equal to 1. Eigenvalues start looking interesting when we start allowing for these values to become complex, and that's when some real quantum stuff is going to take place here. The quantum stuff, again, that's going to, the quantum aspect of this is going to come in the form of when we allow superposition of states, like we've talked on the whiteboard. When we allow for the superposition of states, let's say the superposition of 1 spin up with 5 spin up, then, or 2 spin up with 5 spin up, whatever, then these off-diagonal components are going to encapsulate the amplitude of that superposition. And more aesthetic stuff, and then setting up, this is just the boundaries of the plot, and so much more, right? So this is just more and more aesthetic stuff, and then we write things in, and we print that the animation's been successful. And when it does that, everything should save, as long as you have this guy here, you have your proper path wherever you want the animation to go. That's the path that you put in up here. I just put everything in one file, right? So I have my code with the same name that gets output when this whole thing runs, right? So if I did run this, right, suppose I can run this for let's do a 4x4 matrix. So 4x4 matrix. If I run this, there we go. It's the animation saved successfully. I can go to my matrix animation. Now we have a 4x4 matrix. If we play this, we can see what the eigenvalues do. We can see what the eigenvectors do. So that's a little bit of code for this first episode on quantum statistics. If you like this kind of content, make sure to hit that like and subscribe button, and I'll see you guys in the next video. We're going to start we're going to try to quickly get to very advanced concepts here, but at the same time, we want to take it easy so that we don't get bogged down with too much information all at once. So with that being said, I will see you guys in the next video.